this video, I'll cover k-means clustering. We'll start with what is k-means clustering, the intuition or the idea behind it. Then we'll talk about k-means clustering for one-dimensional data. And then we'll move towards two-dimensional or multi-dimensional data. We'll also talk about distance metrics for k-means clustering. And next we'll talk about optimization or the convergence of the algorithm. We'll also talk about choosing k, the number of clusters. So there is a well-known method known as elbow method, but what are the parameters for elbow method and how do we plot that? We'll see that. And lastly, we'll talk about the few advantages and limitations of the k-means clustering algorithm and few real-world applications. So, k-means clustering is an unsupervised machine learning algorithm for clustering. So, data is not labeled here. In supervised learning, we saw the data was labeled. We had the input features and the labels. But here, the data is not labeled. We need to group similar data. So, data discovers its own structures. So, if before clustering, we just have this raw data without any label, then after clustering, we can get this type of clusters. So, this is one cluster, this is another cluster, this is another cluster. Now, k-means clustering is a hard clustering. What is a hard clustering? In hard clustering, any data point will belong to only one cluster. There is another type of clustering called soft clustering. In soft clustering, one data point can belong to multiple clusters with different probability. But k-means is not soft clustering, it is a hard clustering. Let's start with one-dimensional scenario. So let's say we have few age data for few people and we have plotted the data in one dimension. So we have 18, 19, 20 here, 18, 19, 20. Then we have 27 and 31. Then we have 38 and 40 here. So if let's say k is 3, the number of cluster is 3. So we can then get this is one cluster, this is one cluster, this is one cluster. If k is 4, then we can get this is one cluster, this is another cluster, this is another cluster, and this is another cluster. Consider the two-dimensional scenario. So earlier we just had the age, now we have age and weight. So in x direction, let's say we have the age, and in y direction we have weight. And this is the data we have plotted. So just by seeing the data only, we can tell this can be one cluster, this can be one cluster, this can be one cluster. If k equals to 3, if we want to get 3 clusters. If we want more cluster or less cluster, we can get different clusters. Now, but how a model or machine can find the clusters? So let's start with the one-dimensional scenario. We'll try to apply k-means clustering to find out the clusters. What k-means clustering does is, initially it randomly assigns few clusters. So let's say it assigned, this is one cluster, that means center, this is the center of the cluster. So the cluster will be something like this. This is a spherical cluster it will be. And let's say this is one more cluster centered around this centroid. And let's say there is one more cluster here centered around this cluster. The process will start from here. So let's say this is the cluster centroid we got. Initially, we randomly assigned these 3 cluster centers or the centroids. Now what we'll do, for each of the points, we'll see which cluster is nearest. We'll assign the points to the nearest cluster. So for these 3 points, you see this red cluster is nearest. For these 2 points, this green cluster is nearest. For these 2 points, this purple cluster is nearest. Let's assign the points to the nearest cluster. So let's say these 3 are red cluster, these 3 are in red cluster, these 2 are in green cluster, these 2 are in purple cluster. Now, after assigning the points, you see the center should not be here, right? This center also should not be here. because the points in the cluster is here, the center also should be somewhere around here, right, in the main position. So we have to move the cluster centroids. We have to recalculate the cluster centroids. So let's move the centroids in the correct position. So that's how we get the correct clusters. We'll have to repeat the process again and again to get the correct clusters. So let's see in the two-dimensional scenario. If k is 3, like we want to find out 3 clusters from this data. So let's say we'll randomly assign 3 centroids. So the clusters are basically centered around this centroids, right? So this 3 random clusters we have initialized. Next, what we'll do, for each data points, we'll find out the nearest clusters. For each data points, we'll assign that point to the nearest clusters. So this points will be assigned to this red cluster. Few points here will be assigned to the purple one. Few here will be assigned to the green one. So here we have assigned the data points. These are in red cluster. These are in purple. These are in green. But you see these points are close to the green clusters. These points are close to the red cluster. Right? These are not close to the purple or green cluster. So, but after assigning the points to the closest centroid, our clustering is not complete, right? So this looks like a cluster in our eyes, but these are not correctly assigned. So next, after doing this, we have to do the next step. So we assign the cluster points to the nearest cluster. Then we have to move the cluster centroids to the center position, right? So this centroid will come here, this centroid will come somewhere here, this centroid will come somewhere here for the green cluster. And here we have moved the cluster centroids. We have recalculated the centroids. Again, we'll repeat the next step. What we'll do, for each of the data points, we'll find out the nearest cluster and then we'll assign it to the nearest cluster. So these points will belong to the red cluster only. These points will belong to green cluster only. But these points now will be close to the purple cluster. This also now will be close to the purple cluster. Earlier, these points were close to the red cluster because the cluster centroid was here. Now the cluster centroid moved. Maximum points of the red cluster is here, so that's why the cluster centroid also moved here. So that's now these points will point to the purple cluster. So again, we have reassigned the points to the proper cluster. We'll not stop here. Here you see this, for the green cluster, all the points are here, but the cluster centroid is here. So again, we have to recalculate the centroid. We have to move the centroid to the mean at the center, right? So again, we have recalculated the centroids. So we'll repeat the process again and again and until the clusters stabilize. Now, distance metric. So how do we calculate the distance? We are calculating the distance from a data point to centroid of all the clusters, right? So usually we use Euclidean distance for k-means clustering. It measures the closeness to a centroid. So distance between any point and centroid is calculated using Euclidean distance. So here let's say n is the number of features in the input. That means we are talking about n-dimensional scenario, right? So j equals to 1 to n. That means for all the features or all the dimensions, we are calculating the squared distances, xj minus cj's whole square. This is the Euclidean distance. Now, why Euclidean distance? So the centroid is basically the mean of points, and it works naturally with Euclidean geometry. It produces a spherical clusters. That's what we are creating here. It is fast and computationally efficient, and it's differentiable, which enables optimization. So next, we'll formalize how we are doing k-means clustering, how it works. First, we are choosing some k, the number of clusters. Then we are initializing the centroids. then we are assigning points to closest centroid, then we are recalculating the centroids, and we are repeating this 3 and 4 until convergence. We'll assign points to closest centroid and we'll recalculate the centroid, and we'll do this 3 and 4 again and again until convergence. Eventually, clusters stabilize. Now here we have one algorithm as well. So consider we have the data set D, that is xi from I equals to 1 to n. We don't have the yi, the labels, we just have the input features. And we choose some k, the number of clusters. Then we'll get for k clusters, so let's say C1, C2 till Ck, these are the clusters. We'll initialize the random centroids, mu1, mu2 till mu_k. So these are the random centroids and these clusters initially are empty, right? So we'll assign data points to these clusters. So until convergence, what we will do? For I equals to 1 to n, that means for all the data points, we are calculating f of xi, that is argmin of j, this xi minus mu j whole square. So this is the Euclidean distance of xi and mu j. What is mu j? The centroid of cluster G, right? So this here basically we are calculating the Euclidean distance of xi and all the cluster centroids, and then we are taking argmin of G. That means this is the closest cluster of xi. What is mu of fxi? It's the mean closest to xi. Right, we are getting the nearest cluster centroid or mean. Next, for j equals to 1 to k, that means for all the clusters, what we are doing, we are Cj is xi such that fxi is j. That means initially these clusters were empty, right? So we have to assign cluster points to Cj. So Cj, again in every iteration we are making Cj as all the xi such that its closest cluster of xi is G. fxi is the closest cluster of xi, right? So we are taking all the points that is closest to this cluster Cj. Next we are computing the cluster centroid, right? Cluster mu j. What is mu j? For we are taking the summation of xi in Cj. For a cluster Cj, we are taking all the data points. We are summing up all the data points and then we are dividing it by mod Cj, that means the number of data points. That is the mu j, that is the center of the cluster. So in this part, what we are doing, we are assigning data points to the closest cluster. And in this part, for each cluster, we are recomputing the cluster centroid and assigning proper data points to the cluster. So this we'll do until convergence. Now we'll talk about the optimization, how long this algorithm we saw should run. So in practice, K means minimizes the squared Euclidean distance, also known as WCSS or SSE. What is WCSS? It's within cluster sum of squares, also it is called sum of squared errors. So what it does, so let's say there is this two clusters, right? So for this cluster, you see these are the points and this is the centroid. So if you just see the distances for each of the points to its centroids, these are the centroid, right? So if you sum them up, we'll get the sum of squared errors, right? So this error will get from each cluster. So the sum of squares will get from each cluster and then we'll sum them up for all the clusters. That's how we'll get this WCSS or SSE. How do we calculate this within cluster sum of squares? So WCSS is summation of small k equals to 1 to k, that means for all the clusters we are doing summing up this. Then summation of x in cluster k, that means the data points in the particular cluster k, x minus mu k square. This is the Euclidean squared distance of the points and the centroids. So for this cluster, if we consider, these are the point x points. So x is the data point, mu k is the centroid of cluster K. Right, for all the points, we are calculating this squared distances, that is within a cluster, right? And then we are summing them up for all the clusters. So, right, so if WCSS for cluster 1 is, let's say, 89.5, and for cluster 2 is it is 115.6, then the total WCSS will be 205.1. So we are calculating the square distance within a cluster and then we are summing them up. Now lower WCSS means tighter clusters. Why? Because we are trying to minimize this, right? So if we minimize this, all the data points within a cluster will be closer to the centroid, right? And that is, we'll have tighter clusters. Now, when our optimization stops, we are doing this process again and again, right? So we are assigning data points to nearest clusters and then we are recalculating the cluster centroids. Like, when should we stop? So optimization stops when any of this follows. So if you use any model libraries for k-means clustering, so they follow this. So if after some iterations, if you see the centroids stop changing position, so then also we can stop. If cluster assignments stabilize, if the data points, we are assigning the data points to the cluster, right? If this assignments doesn't change after some time, then also we can stop. WCSS improvement. So we are trying to minimize this WCSS, right? So that we get tighter cluster. So if this WCSS becomes less than some tolerance like epsilon, right? Then also we can stop. Or otherwise some predefined max iterations reached. So if we have defined like 100 iterations or 200 iterations maximum, if we have reached that limit, then also we can stop. So if any of this occurs, we can stop k-means clustering. Now choosing K, how do we choose the number of clusters? So we have this well-known method called elbow method. We'll discuss that now. So what we do here is choose different small k value for this cluster numbers, right? And we'll plot the within cluster sum of squares. So in the x direction, we have taken the number of clusters. In the y direction, we have taken the WCSS, right? We are trying to minimize the WCSS, right? And then we'll look for bend or elbow point. So you see, this looks like a elbow and this is the elbow point. This looks like the elbow in our hand. And that value, you see here, this is the 3 here for this case, that value will be the optimal K. Now why it works? Our target is to minimize the WCSS, right? The within cluster sum of squares, right? So initially, when we have just one cluster, that means all points are assigned to only one cluster. And when we have just one cluster, WCSS will be maximum. Because the sum of squared errors, we just have one cluster, the distances, squared distances will be maximum. Now we are increasing the number of clusters, right? So what we see here, this WCSS rapidly reduces here until this point. After that, the change is not that rapid, right? So that's why we are choosing this elbow point, right? This looks like a perfect value for our number of clusters. Now, few advantages of k-means clustering. It is very simple and fast. It works well on large data sets. It's easy to implement and understand. That's the main point. Now, it has few limitations as well, like we need to choose k, right? That is some extra overhead here. And since it's sensitive to outliers, so if we have outliers, like these are the red cluster points and this is the blue cluster points, right? But if we, let's say we have few red points here as well, our clusters, our k-means clustering will not work properly here. So now next is, it works best on spherical cluster, right? We are having the centroids and the clusters are centered around the centroid. So if the clusters are not spherical cluster, then also this k-means clustering might not work properly. Random initialization may affect results. So we are initializing the centroids randomly at the beginning point, right? So that also might affect the results. But despite all these limitations, k-means clustering has lots of real world applications. I have just pointed out few here. So customer segmentation in marketing. So if you want to segment different customers, we can do that. Image compression. So here similar pixels will be clustered together. So we can use k-means clustering also there. Then anomaly detection, document clustering, all these cases, and also there are few other, many other use cases for k-means clustering.